So, now so these are the roughly the various kinds of timers available, and now we take a look at what is known as the counter. Okay. So, now the counter is nothing but, frankly speaking, the counter is nothing but a timer with an external pulse. So, now in the counter also, there are two registers, one is called a preset register and another is a count register. But only thing is that in the timer, the timing register is incremented by an internal clock at regular intervals of time. So, the timer is nothing but a counter which counts the timing pulses from an internal clock. While for the count register, for the counter, this count, you are trying to count something, maybe the number of parts produced or the number of parts arrived on a conveyor or something like that. So, in which case, with every event taking place, there is you have to generate some kind of a pulse using again contacts and sensors. Now, those external pulses in this case will actually augment the count register. So, that counter is in place of the internal clock pulses which were coming at the timer, here we have external pulses which are triggered by the events that we want to count. So, again you have enable reset logic, same thing. In this case, we have what is known as a count logic rather than a timer run logic. So, the count register is incremented by 1 every time count logic goes high. So, every time this goes high from 0, the count register is incremented by 1. And just like the previous case, when the count register value exceeds the preset register value, at that time the terminal count is reached and the output coil goes high. So, this is the meaning. In some cases it may be a down counter, in which case the count register may be loaded with a preset register value and it may count down to 0 every time a pulse comes. So, it may be an up counter or it may be a down counter, or it may have up and down count inputs by which it can have. It can be also an up down counter. Some basic a very simple example. You have a conveyor into which parts are supplied. So, parts are coming from either this machine B, or parts of type B are coming and parts of type A are coming. So, you want to implement this logic that run conveyor when parts x parts of A, at least x parts of A and y parts of B are on the conveyor, at that time the conveyor will run. So, this is what we want to program, and the arrival of a part of type B is asserted by this and arrival of a part of type A is asserted by these two sensors. So, what is the logic? So, here is so this is an example of using counters. So, you see that we have two counters. First of all, this is the master switch. The moment it goes on, this output is asserted. Now, this now see that when IN001 is asserted, this IN001 also is asserted, and this IN001 is also asserted, and this IN001 is also asserted. So, when this is 0, everything is 0, but when this goes 1, then all these rungs are enabled and both the timers are enabled. Now, the arrival of part of type B is signified by this, and arrival of part of type A is signified by this. So, this is for A and this is for B. So, every time a part arrives, there is a pulse here and the corresponding outputs are incremented. And now, when so the registers are incremented, not the outputs, the registers are incremented. So, when the registers when this register crosses, this output goes high. So, it is in series, So, OP003. So, when you put them in series, you want that both of them must reach their preset count values, only then the conveyor will run. If you put them in parallel, it means that if any one of them reaches that preset value, then the conveyor will run. So, this is an example where we can use a counter for an industrial problem. This is a nice example of counting how many parts per minute are going on the conveyor, let us say, which in a way indicates that what is the production rate. So, it may be an important management information to display what is the production rate. So, now therefore, so we want to count how many parts per minute. So, we want to not only count parts, we want to also count it only over 1 minute of interval after we have pressed start for this operation. So, obviously, for creating this 1 minute interval we need a timer, and for counting the parts we need a counter. Therefore, it is a mixed timer counter example. So, here we have the timer and here we have the counter, both have their, here it is loaded to 60 because we are talking about minutes and we are assuming that the internal clock pulses are available at every 1 second interval. So, now suppose IN001 is a switch which one can press when he wants a measurement that over the next 1 minute how many parts pass. So, when these two are when this measurement desired contact is enabled, at that time both this timer and the counter are enabled. Now, what happens is that so when you say start, this is a kind of master switch, then when you say start time, so you want to know within this time of how many parts have passed. So, you start time, so this goes high and this goes high. Now, this does not go high. So, this is low. So, now and when this is on, this is also on. So, now every time a part arrives, you get a pulse. So, the counter goes up in the meantime, after the time has expired, OP001 goes open, goes off. So, this goes to 0 and then further parts are not counted. So, this when this is going to 0, when this becomes open, whether this here you get a close or not, it does not matter, this cannot be 0 because these are in series. So, therefore, at that time you in the counter you have the value of how many parts have passed over the conveyor in the last minute. These are, so we have covered the timer and counter in some detail. Now, we will take a very brief look at, there are arithmetic instructions, there may be logical instructions, specifically instructions like compare, instruction like doing ANDing, ORing. So, all these instructions are available just like a low level language, and you can express them in various formats depending on the manufacturer, as I said. So, in our format, we are saying that by this diagram we are saying that this, if you put this rung, it is a rung for doing the it will, when this rung will be executed, basically two operands, operand 1 and operand 2 will be added and their sum will be put at the location sum, provided this enable logic is on. And this output coil may be used for various purposes. One of them could be that if there is an overflow, that has occurred during the summation, then it could go 1. So, it can indicate an error condition and then be used in the further logic. So, this is just an example of add. Similarly, you could have sub, you could have multiply, you could have various other things. This is just one example of an arithmetic instruction. Next is data move. So, if you want to, again you depict it as a rung, because in the RLL everything is a rung. So, in this case you have again the data move will take place depending on whether the enabling logic is satisfied or not, and then data will move from source to destination, and maybe if there is some address failure or something, then, or maybe after the data has moved, actually this can become 1. So, this can also be used for indicating condition after execution. You can have, so this is a data move, you can have various other functions, like you can have bit manipulation functions, you can have various kinds of block moves, etc. You also have various kinds of logical instructions. So, apart from data transfer, the last instructions which are very important are program control instructions, by which we want to control, we do not want to execute all rungs of the RLL at all times, but rather we want to control whether we can skip some of them or enforce some of their values. So, we have typically, to give an example, we have a skipping facility, which, so when this is enabled, then this skip 001, this is a very special type of contact. So, it is enabled. When it is enabled, then what it means is that the next n rungs, so you have skip 001 and n is a parameter. So, it means that the next n rungs will not be evaluated, they will when this is high, this is the meaning. So, it is like, it is like if skip not equal to 1, then, so this is like if skip not equal to 1, then this will be executed. If skip is equal to 1, as long as it stays 1, the the next n rungs will not be evaluated and they will be maintained at the old value. Similarly, you can have another facility which we call the master control relay, which means that here I mean this is also a program control statement, and it means that whenever the enable logic is satisfied, then this MCR output coil, which is a very special output coil, is excited, and which means that the next n rungs will be set to their outputs. Each one of them has an output coil here, which I have not shown. So, the next output coils, these output coil values will all set to 0. So, without evaluating, irrespective of the logic in this branch, if this is excited, then they will be all set to 0, but if this is not excited, then they will be evaluated normal, like normal rungs according to normal PLC logic evaluation. There are some special instructions which also are there in a PLC RLL program language. For example, this is a sequencer. So, a sequencer, this is actually the sequencer, this is the sequencer. So, the sequencer is a block which can be separately programmed and which nicely executes a sequence of steps every time it is excited. So, let us see what is happening here. So, first of all, this is a master switch which will become on. Let us assume that and suppose this is off. So, first of all what happens is that this goes high. When this goes high and this is already low, so therefore, there is a path from this place to this place, and even if this is taken off, this path maintains. Whenever there is a path here, immediately this is enabled and this is enabled. So, when this is enabled, what happens is that when this is enabled and this is now reset. No, this is normally closed. Oh, this is normally closed. So, when this is closed, it is already enabled because this is off. So, therefore, and then this OP001 goes on. So, when this OP001 goes on, it starts timing. So, after a preset timing, this OP003 will go high. Now, when this goes high, immediately what happens is that you get a pulse here. So, in the sequencer every time it gets a pulse into its step input, it executes a particular set of outputs it will exercise. Okay. So, a particular set of outputs which are bit outputs which are stored in some register. Okay. So, there is a start register. So, there are sequence of registers. Every time a pulse comes, a new set of register outputs. So, you have register, maybe these are 3 different or 8 different valves. So, you have stored some values. So, maybe when in the first step this is 1, this is 1, this is 0, this is 0 and this is 1. That is the way you have programmed it. So, when step 1 is executed, then these outputs will actually go to the feed. So, the first pulse has come and the first step is executed. After the first step is executed, in the meantime you see that so the first step is executed and it is waiting there. Now, when this has become 1, immediately this becomes 0 and it becomes 0 again. So, again it is enabled. So, now what happens is that an output 001 is already on. So, therefore, again it times. So, basically what is happening is that it is with this arrangement it is continuously timing, and then the moment this OP003 goes high after the timing interval, this gives a pulse here. So, a step is executed in the sequencer, and then because it is latched like this. So, immediately when this goes high, this is again becoming reset, and then once it is becoming reset, it is this one is enabled, and therefore, it is again timing. So, it is generating continuously generating some timing intervals, and at the end of each interval you are getting a pulse which is executing the start register, executing the sequence register of the sequencer. At the end of the sequence has a fixed number of steps. So, at the end of the sequence this will go high. So, once this goes high, then what happens is that this one goes off. When this one goes off, then this one goes off, and when this one goes off, then there is no more timing here, and this itself, that is the sequencer itself, is disabled. So, this is the way a sequencer works. Now, so this is what is expressed here. So, if you press start button, IN001 is a start button, IN002 is actually a stop button. You could make the sequence stop at any times. So, initially all output coils off, then IN001 pressed, then output 001 on and latched, then sequencer enabled, then timer starts timing, then at terminal time output 3 goes to high, and immediately sequencer steps and timer resets and immediately starts timing again. That is what we explained, and this cycle repeats. At the end of the sequence OP002 goes high, which means that the OP001 goes low and the sequencer resets and the timer stops timing. So, this is how it works. So, we have come to the end of the lesson, and in this lesson we have seen the various timers and counters, and we have also seen some arithmetic data move and program control operations, and finally, we had seen other macro operations like a sequencer. There are sometimes even some other continuous mode operations also like PID etc., which we have not seen so far. So, coming to the end, we have the usual points to ponder. For example, you could try to modify the die press controller such that a delay is introduced between, that is, after the master control switch is put on and the up solenoid goes on, there is a delay. You can try to put that by modifying. Similarly, you could also modify the die press controller such that the number of die press cycles is actually counted. So, you say that after every 1000 presses you want to stop the machine and you want to maintain the machine. So, you want to count every time a complete cycle of die, there is one going up and one going down, is completed, and you want to count them, and after it reaches a count, you want to stop the machine for maintaining. Similarly, you could improve the RLL program, which we said in our earlier points to ponder, RLL program for control of a pump to keep the water level in a tank by introducing a hysteresis in your on off control cycle, and also sampling the water level every 30 minutes, that is not continuous sampling the water level every 30 minutes. So, that is all for today. Thank you very much.